The first part, properties of solid, liquid, and gases. Let's quickly take a look at that. First of all, we understand what matter is. Matter is anything that has mass and occupies space. So, and there are three various states of matter. We have the solid state, the liquid state, and the gaseous state. This is understandable. And we say, look at this is a sample of solid. You can see all the particles are tightly put together. Solid has a fixed shape and a fixed volume. Everything is tightly put together. But in the case of liquid, the liquid has a fixed volume but does not have a fixed shape. It takes the shape of any container you put it into. If you pour water in a circular container, it will take the shape of that circular container. If you pour it in a cylindrical container, it will take the shape of that container. If you pour it in any shape, it will take that shape. Triangular container, it will take that shape. So it doesn't really have a fixed shape, but it has a fixed volume for liquid. The gas expands to completely fill any container you put it into. You just put a little gas in a container, it will expand. You cork it, close it so that it will not escape, and then you see that the gas will quickly occupy everywhere. Okay, it expands very quickly and fill, no matter the small gas, it will fill the whatever shape that you've put it into. That's why perfume, if you use perfume is a gas, by the way. So if you spray very good perfume, you see that it smells around, like it goes around even beyond your imagination, beyond the room, beyond, it fills up the whole space. So because it's a gas. So gas particles, they expand very rapidly and very quickly, and they move around and they cover the shape of any container that you've given it to. So these are the properties, like we've said already. The solids, they have a definite shape and a definite volume. The solid cannot flow because they cannot flow, and they are not compressible. Reason because the particles are tightly put together. The particles are already tightly put together, so you cannot compress things that are already compressed. Like, things that are superimposed upon each other. You cannot compress them anymore. Okay, so that's why solid cannot be compressible and it cannot flow. It cannot flow because the particles do not have space to overlap. They don't have space to overlap each other. Okay, they tightly close together. They only vibrate when you supply heat to them. They only vibrate about their fixed position. Now, in the case of liquids, they do not have a definite shape, but they do have definite volume. Well, the amount is the amount. The amount of volume they have. If you take, like, for example, if you use a measuring cylinder, we use measuring cylinder for measuring volume, or you use a burette for measuring volume in chemistry, or use a pipette for measuring volume. For example, if you measure a certain volume, let's say 250 centimeter cube of water or of any liquid, and that's it. Whichever container you put that 250 is still 250 centimeter cube. Okay, so they have definite volume, but they do not have definite shape. They take the shape of any container you put in, as we've itemized already. Liquids are able to flow, however, they are able to flow and they take the shape of any container that you put them to, although they are not compressible, because the liquid particles are not super far from each other. They are not so far from each other. They are also close. It's just that they are not as close as that of solid. So they only slightly slide over each other. So they really cannot flow. And they really cannot be compressible, but they can flow. They really cannot be compressible. Now, in the case of gases have no definite shape, and they do not also have definite volume. You put little of them in a shape, it covers it up, it fills it up, it travels very fast, and it covers everywhere. Okay, gases, they can flow and can take the shape of any container, and they're highly compressible. You can compress gases and it takes the shape of any container and it can flow. Okay, now let's go to change of state as quickly as we can. We say change of state, when a substance changes their state, then the number of molecules in that substance does not change. The molecule itself remains the same, but it's only that the distances has been created. The molecule do not change. The number of molecules remain the same. The number of atoms in that material remain the same. Their mass remain the same. Their mass does not change. Okay, mass remain the same. Mass does not change. But what only changes is that the distances between one molecule to the other, or the distance between one atom to the other in that in that substance. So distance has been created, maybe due to heat. The particles are a little bit further apart now. That's what changes. But the particle, the mass of the particles do not change, and the number of particles do not change. So when the particles change of state, usually due to heat or due to cooling, then the only thing that changes is that distances between molecules increases. The distance between one molecule and the other molecule increases, but the number of molecules do not increase. Neither do the mass of the substance increase. The mass of the substance does not increase, and the number of molecules does not increase. The number of atoms does not increase. The only thing that increases when the substance change state is that the distance of molecule now increases, meaning the molecule will move a little bit further from each other. For example, if you take a look at solids, in this diagram, you can see that the molecules of solids or the particles of solids are closely packed together. They are closely packed together. They hardly have any space between them. They are closely super packed together, right? But when you melt it, how do you melt it? You supply heat. You heat an ice. If you heat an ice, it will start to melt. And then you see distances are created. The particles or the molecule can slightly move over each other, right? And then if you continue the heat, after a certain time, at a certain temperature, the molecule will start to boil. The substance will start to boil, and greater distance now comes in. The molecules are now farther apart from each other, super farther from each other. Okay, so melting occurs when the solid turns into liquid. In the case of ice, you heat ice, it will melt and it changes to water. Freezing occurs when the liquid turns back to ice. When the liquid turns back to solid. So for example, if I take this liquid and I put it in a refrigerator, after some time it will freeze. Why? Because the molecules will now be brought together so closely. Okay, now let's move on quickly. Any question?
No.
Okay. Then boiling is when it usually occurs when the liquid turns into a gas or turns into a water vapor, or in the case of water, if it turns to water vapor, or what we call steam. If it turns to steam, then we say boiling is taking place. So when you keep heating a liquid, it will at a point in time it will start to boil. The temperature for water, the boiling point is 100 degrees Celsius. 100 degrees Celsius. So when the temperature of water hits 100 degrees Celsius, then the water will start to boil. Bubbles of water will start to, and steam will start to escape if you don't cover the pot. The steam of water will start to escape. And that's what we call water vapor. Okay? So that's boiling. Now, condensation or cooling or condensing is when you collect the steam and then you start to let it to cool down. After a while, it will cool down to become liquid. You cool it in refrigerator. You put them in refrigerator. Not this time around, you don't heat it. You put it in a freezer or a refrigerator to cool it, and then first it changes to liquid, and then you keep cooling it. Later it will freeze and become an ice block. Okay, so that's that for that. Let's move to the next one because it's super a lot and we have to cover it up. Now let's go to the molecular matter. Let's talk about the same thing we've talked about, but with reference to them in terms of molecule. Now let's first of all look at the arrangement of molecules, motions of particles. First of all, let's see the arrangement of solid. In solid, the molecules are very close together and they are arranged in a very regular and fixed pattern. They are arranged in a pattern that is very systematic. Okay, they are very systematic. You see this molecule, the next one, they are very systematic. The arrangement is very organized. The particles or the molecules are very organized. They are regularly organized. The pattern is very definite. Okay. Then we say the molecules, how they when you supply heat, how does the heat pass from one part of it to the other? The molecule vibrates and pass on the heat. You know, the molecule vibrates in a fixed position, but the electrons in the molecules are able to pass the heat. So two things are happy to pass the heat. The electrons, the delocalized electrons or the free mobile electrons, helps to pass the heat from one atom to the other in the substance. And another thing is the atom itself, or the molecule themselves. Okay, when they get heat, they vibrate. Vibration helps them to pass. Because when they vibrate, they touch each other. Then by so doing, they're passing the heat from one part to the other. That's why when you use a spoon like a stainless spoon or a silver spoon to cook without a handle, and after a while you're using it to turn the food in the pot. After a while, if the spoon does not have a wooden handle or a plastic handle, after a while the spoon itself will burn your hand, because the heat from the pot passes from the tip of the spoon and goes into the spoon, and the heat move from one molecule of the spoon to the next molecule to the next molecule till it gets to where your hand is, and then you feel the heat. So this is what happens in solid. This is what happens in solid. We say the molecules are close together, and they are arranged in a very regular pattern. And then we say this molecule only vibrates about their fixed position. And there are two things that carry on this heat energy from one part to another. When you study conduction, the heat transfer, when we look at heat transfer, the three methods of heat transfer, we will talk about the conduction, convection, and radiation. And then we will still a little bit talk about this. So the two techniques by which the heat is passed on from one molecule or from one atom. I can use atom and molecule interchangeably, or even ions. We can use them interchangeably. Okay, we are referring to same thing or similar thing. Okay, I will be using them interchangeably, so don't get confused if I say molecule or I say atom. It can be used vice versa sometimes when we are generally explaining this concept. Okay, so when the molecule vibrate about their fixed position, then they pass on the heat from one molecule to the other. The molecule that gets the heat, when it vibrates, it touches the other molecule, the heat passes on from itself to the next molecule that it touches. And then like that one starts to vibrate. Anyone that gets the heat will vibrate. When it vibrates, it passes on the heat to the next one. So the heat gradually begin to spread. That's one way. Another way by which the heat is passed on is by the electron, free delocalized electrons. Because every atom or a metal, or in most solid, we have what we call the delocalized electron, especially in metals. These delocalized electrons or free mobile electrons also help in passing the current from one point to another. Is that okay? Now, in the case of liquid, we say the molecules are still close together, no serious gap, but are not so close, and they are no longer arranged in a very regular pattern like in the case of solid. See, they are no longer arranged in a very regular pattern as in the case of solid. Is that okay? But they are close. Even if they are not super close, they are close. And then another thing is that the molecules are able to slide past each other for liquid. In the case of liquid, the molecules are able to slide past each other. Okay? So that's one characteristics of a liquid. So we talked about their motion, as if they are able to slide. Liquid molecules are able to slide past each other. That's the movement. That's in their movement, how the molecules move. And then we also talk about, in solid we say vibrate. That's their movement. Vibration is their movement. Okay, but we also talk about their arrangement. We say they are close. The arrangement, the molecules are close together, and there are no serious gap between the molecules. Now, and then the molecules are able to slide past. We've talked about this. Now, in the case of gas, we say the molecules are widely separated, super separated, about 10 times the farther apart in each direction, about 10 times farther apart from every direction. So if you look at it, you see the distance are huge. This is just a sample, okay, a sample. Okay, the distance between one molecule and the other in the case of gas is huge compared to liquid. Liquid has little distance and the arrangement is not very regular. Okay, so they're able to slide past each other gradually. But solid, they are fixed. Molecules are fixed in position, they only vibrate. Okay? Then let's talk about the movement of gas. We've talked about their arrangement. We said they are widely separated. That's their arrangement, about 10 times further in each direction to each other. Now let's talk about their direction, their movement. Right? We say they move very randomly. Gas, they move randomly. They collide with each other and they collide with the walls of the containers. they collide, they bounce off. There's a lot of collision. They bounce here, turn, change direction, move here, go left, right, center, bounce up, down, this, up. So this is how they move. They're very random. It's not systematic. It's not very regular. So they move randomly at a very high speed. That they bounce here, bounce there, and so on and so forth. Is that okay? So let's quickly look at the forces and distance between molecules. And this is for extended. The forces and distance between molecules. The force between the particles affect the state of matter. It determines what state of matter that substance will be. If the force is very strong, it's very big, it creates a big bond between them. If it creates a huge super bond, then we can say that could be solid. Okay? So the forces determine actually the state of matter. The forces, if there is a very strong van der Waals forces or very strong intermolecular forces holding the molecules together, like in the case of solid, then such substance will be in the state of solid. If there is a very strong what we call van der Waals forces or very strong intermolecular forces, then it will remain in that state of matter. Is that okay? It will be in solid. It will be in solid. Now this is because the magnitude of the forces affect the relative distances and the motions of the particle. So if the force is very strong, then the particle cannot move. They will only vibrate about phase position. If the force is a bit weak, then the molecules can slide over each other relatively. If the force is very weak, very, very weak, like in the case of gas, the molecule can just be bumping up and down like people with too much freedom that will lead to destruction. That's why actually gas molecule they are self-destruct. They move randomly, no direction, ceaselessly, zigzagly, and they hit themselves, they bump. They are like constantly making accidents. It's like, if you look at, it's like a car just hitting pole, pillar, everywhere, bounce here, go here, hit this, hit that. That's the same similitude with the gas molecules they possess. So they're just bumping left, right, center, hitting the walls of the container, hitting themselves, bouncing up and down, no direction, no sense, no wisdom, just everywhere, okay? Why? Because the force that is supposed to hold the molecule in a position is very, very weak. It's super weak. So if the force determines the state of matter that a substance will belong or will be. If the force is super strong, then that matter or that substance is a solid. If the force is a bit weak, then it's a liquid. If it's very, very weak, then it's a gas. Is that okay? Now let's take a look at we say this affects the ability of the substance to change shape. Yet the same force is also responsible for how the substance can change its shape, how it can change its volume, and how it can flow. So if it's a very strong force, it's difficult to change the shape, change the volume, and also flow. If it's a weaker, these things can happen slightly, and if it's a very, very weak force, then these things can happen very fast and very rapidly. Now the particles that makes up matter includes atom. I told you we can use it interchangeably. I can be using atom, molecules. These are particles. In the general term is particles that we use, but in more specific term we use the name atoms, molecule, ions, and electrons. So every matter or every particle, every matter contains these kinds of particle. A group of atoms are called molecules. Okay, a group of atoms are called molecules, and atoms that have lost electron or gain electrons, they are called ions. Atoms that have lost electron or gain electrons, they are called ions. Those electrons begin to move about, bump around like freelancers. Okay, now let's talk about the intermolecular forces and the motions of I think technically I've spoken about this technically, but let's just quickly have an overview. So in solid, let's talk about the intermolecular force. I told you that if the force is very strong, then the substance holding the particles together, then the substance is a solid. The molecule in solids are held in place by strong intermolecular forces. We call it strong intermolecular forces or van der Waals forces. they only vibrate in a position and the distance between them is fixed. Okay, the distance does not vary, it's fixed in position, and this gives the solid this ability, or what it is, how rigid, the rigid shape it has is because of this strong force that is holding the molecules together, and how the fixed volume it has is because of these strong intermolecular forces that is holding the molecules, or the ions, or the electrons, or the particles all together. Now, in the case of liquid, the molecules in liquids have enough energy to overcome the forces between them. The molecules in liquid, they have what we call enough energy to overcome the forces between them. The molecules themselves have enough. So that's why they're able to slide past each other. They're able to break loose and slide past each other. Although they are still held close together, but the molecule themselves, the internal energy of the molecule enables them to be able to move, to withstand the force that is supposed to hold them together. Now, this is like two things. The force is holding the molecules together. Between one molecule and another, there is a force, what we call the intermolecular force, that is holding them together, bonding them together. But the molecule have its own internal energy. This internal energy comprises of its potential energy and its kinetic energy. This internal energy of the molecule comprises of its potential and its kinetic energy. In the case of liquid, the internal energy is sufficient enough to cause the molecule to slide slightly. Not like super movement, but slightly. They can slide past each other. Is that okay? Just a minute, let me sip water. Okay.
Sir, you can skim through. You don't have to explain in detail. I already understand. Just for a quick recap, it's fine.
Okay.
So we have past papers. You don't have to explain in detail.
Okay. So for gases, we already measured all this one. The gases, they have more energy, internal energy, to move the molecules, the atoms or the molecules, and they move randomly at a very high speed. That creates a big distance between these things, and they're able to move. Now, here comes a question. It said two states of matters are described below. Identify each of the states of matter. Substance 1, molecules are spaced very far apart. Molecules move very quickly at random, and molecules move in a straight line. And then there's substance 2, molecules are quite closely packed together. Molecules move about at random. The molecules do not have a fixed position. So what is substance 1 and what is substance 2?
Substance 2 is gas.
Look at it again. Look at it again. They said it in a way to confuse, especially the second point.
It's gas. Substance 2 is gas.
What's substance 1?
Wait. Then substance 1 is gas?
Yeah. So what's substance 2?
A liquid?
Yeah. Correct. See, they've answered it. Substance 1 is gas. He said this can only describe gas, right? This confirms that substance 1 is gas. And then substance 2, this confirms that substance 2 is liquid. Okay, so they've answered that. And let's go to temperature energy of molecule. Okay, we say first of all, temperature is the degree of hotness and coldness of a body of an object. The degree of coldness and hotness of an object. We want to look at temperature and the energy of the particle. The heat energy results to whatever temperature, amount of heat energy that a substance has, result to the amount of the temperature that it will have. So the amount of pressure that a gas exerts on its container is dependent on the temperature it has. So if the temperature is small, if you supply heat, or if there is no heat, if the temperature is very low, then you see that the collisions of molecule in a substance is very less. There is less collision. So since there is less collision, then there is no much pressure, because pressure is a result of collision, frequent collision of molecule bumping onto each other and hitting the walls of the container. So the higher the temperature, the more the speed of molecule, and the more the average kinetic energy they get. And the more the average kinetic energy that this molecule get, then the more the frequent collision. And the more the frequent collision, the more the pressure, the greater the pressure. Is that okay? So you can see we start from temperature, you give temperature, and then it will increase the speed of molecule. Speed of molecule will increase the average kinetic energy. Average kinetic energy, when it's increased, then there is more and frequent collision. And when collision is very frequent, then pressure is increased. There is greater pressure. Is that okay? So kinetic energy is a big factor in determining the pressure of a substance. And this kinetic energy will increase if you increase the temperature of the molecules. So, and temperature increase when you increase your heat that you supply to a system. So as temperature increases, speed decreases. As speed decreases, so we can itemize them here. So we say, it's like you say temperature okay, it's like we say temperature when it increases, the speed will increase. Speed of molecules will increase. When speed increase, we say the average kinetic energy, Ke. So kinetic energy, I write Ke, increases. When the average kinetic energy increases, we say collision will increase. When collision increases, then it will result to greater pressure. Pressure will increase. This will lead to increase in pressure. This will result to increased pressure. Okay, you can see, so from temperature increases, here you can be putting increase. Here increase, temperature increase, speed decreases. When speed decrease, when speed decrease, kinetic energy will increase. When kinetic energy increase, then collision will increase. When collision increase, pressure will increase. Okay, so that's that for that. Let's move on quickly. Is that okay?
Yes.
So the same thing will happen as the temperature of the system decreases. You see the pressure will also decrease, because everything will be going in the reverse. If temperature is decreasing, the pressure will decrease, because if here is decreased, speed will decrease. If speed is decreased, kinetic energy will decrease. If kinetic energy is decreased, collision is decreased. When collision is decreased, pressure will decrease. But in textbook, they will just tell you, oh, temperature increase, pressure increase. Sometimes you need to get this in between. See, these things are put in between. Okay, when temperature increase, they say, oh, pressure increase. When temperature decrease, pressure decrease. But we need to know in between how it leads to it. Okay, that's that for that. Okay, now let's see some of the work that was done by this Yugoshoko mathematician and the physicist Lord Kelvin, who designed one of the units of temperature. Okay, and he came up with this, what we call the Kelvin scale. And then he said this absolute zero temperature is equivalent to negative, what we call the negative 273 degrees Celsius, the absolute zero. So this Yungu guy came up with this temperature, and when we make a plot of pressure, the pressure of a given mass of a gas, this is called pressure law. So when you plot a pressure law, when you plot pressures on the vertical axis against temperature on the horizontal axis, you get a straight line like this going to the negative side of the graph. And if you touch the graph at minus 273, this point is called the absolute zero. The absolute zero. Negative 273 is called the absolute zero value of temperature. Is that okay? The absolute zero. That's called this place. The absolute zero is called negative 273. So this is what this Yungu guy came up with, and today it's used as one of the units of temperature. Now let's go to the next one. Motion of particle in gas. Okay, this one I think we already know. In a gas, we say the particles, they move randomly, they collide with each other, they move at high speed, they heat themselves, they heat the walls of the container, and they heat the molecules, they also heat the container. And this will happen, their movement will increase if you increase the temperature. And why? Because all of these things that we've mentioned also increase. When you increase temperature, speed of the molecules or the atoms will start to move at higher speed, and then that will increase the average kinetic energy, because once you are moving at higher speed, your kinetic energy will increase. Once you gain more kinetic energy, there will be more frequent collision between particles and the walls of the container. When this happens, or when this continues to happen, then we have a greater pressure. So this is what we have here, other motions of particles. Let's move quickly. Now, pressure and forces of particle in a gas. So we have related pressure. We said pressure is related to force. By say pressure of molecules in a gas is the force per unit area. Is force per unit area, meaning the force is that particular thing, that heat. The molecule hit the wall. That heat, slap, kick, push, pull, they are all forces. So when molecule hit the wall, that's a force. When it hit another molecule, it's with a force. So, but the specific place it hit, assuming this is a molecule, and this molecule decided to be moving because of heat, or the speed has increased as a result of increase in temperature. This molecule bump, they move every direction. It bumps here and hit this place. So when you hit, you hit a specific area. That place you hit is called the area A. So the force with which you hit, that heating capability is called the force. So if I divide the force by the area, that will result to what we call pressure. That will result to what we call pressure. So force per unit area is pressure. Okay, force per unit area is pressure, and the unit is Newton per meter square, or what you call Pascal. Newton per meter square, or Pascal, PA. Named according after the scientist that invented this. Is that okay? Pascal. So this is what is happening. These molecules, when you heat this whole thing, they gain more kinetic energy, before they get their speed will increase when you hit, and then they get kinetic energy, and then collision rate of collision will increase, and then the more heat per unit area, more heat the surface per unit area, that will result to greater pressure, because the more heat capability per unit area, the more molecule heat per unit area, the greater the pressure of the molecule of the gas. So this is what is explained here. So a feature of gas is okay. Say for pressure is force over area. The area is in meter squared. The force is in Newton, and the unit of pressure is Pascal. Or you can say Newton divided by meter squared. Is that okay? So this is the heating capability. See, they heat here, they bounce this way. This one is coming this way, heat this place, bounce off. This one come here, heat here, bounce this way. So every time there is heat, there is a force. Whenever a molecule, see, whenever a molecule hit the wall, this is like the wall of a container, a boundary. Okay, whenever a molecule hits the surface or the wall, there's a force, because heaty, kicky, pushy, all of these are forces. So when molecule heat, there is a force, and it also hit a spot. That spot is called the area. So when you divide the heaty amount of heat divided by the space, the area of the space you heat, you get the pressure. Okay, you get pressure. Pressure is force per unit area. Is that okay? So let's see the Brownian motion. When you want us to stop for this thing, you let me know, okay?
Okay.
Yeah, when you want us to go for questions, you let me know. Otherwise, we'll still be revising like this. Okay, so Brownian motion. First of all, like we already explained, we say molecules, they move randomly, zigzagly, hit themselves, and hit the walls of the container. Now, this one is very evident. According to Robert Brown, the experiment carried out using the polygrains in water. Okay, so he saw this under a microscope, and see the movement of the poly in water and how they hit themselves and hit the walls, and they move randomly using a microscope. So he was able to view this. Another way is to look at the motion of the smoke particle air molecules. You can take some smoke particle, put in a glass jar, and also supply air, allow air to go in, and then you put a light source, and use microscope to look at view from the top. You see how the smoke particles are being bombarded by the air molecule, or how they are bombarding the air molecule. This type of motion is called Brownian motion. The random movement of a smoke particle, or one particle against the other. The random bombardment of one particle against the other. For example, a good example is the smoke particles and the air molecules. Okay, they hit themselves, they hit the walls of the container, creating a very dynamic and random movement. For example, this diagram is showing the smoke particle, a sample of a smoke particle, and these tiny ones are showing the air molecule. When you say gas molecule, it still refers to air molecules. So you can see this air molecule, they are hitting the smoke particle from all directions and pushing it up and down, hitting it, striking it. So this kind of motion, they creating a lot of collision and random movement of the smoke particle. This type of motion is what we call the Brownian motion. It's what we call the Brownian motion. Here is a glass jar, or an enclosure where you have the air molecule that are smaller and they are moving faster, and then you have the smoke particle, larger particle. So this smaller one will hit the big one will keep being pushed up and down by these small air molecules. So that's for Brownian motion. Now let's move to what we call the gases and the absolute temperature. Okay, we've introduced temperature. We said the instrument for measuring temperature is a thermometer, We have different types of thermometer. That's a topic for another time. Where we have the liquid in-glass thermometer, we have thermometric thermometer, and so on and so forth. But we're going to look at the temperature scale, the different scales that we use for temperature. Okay, we have the Kelvin temperature scale, and we have which begins with the absolute zero, and the absolute zero, that's 0 Kelvin, is equivalent to negative 273 degrees Celsius. The 0 Kelvin is so we have two scales, three scales actually. We have the Kelvin scale, we have the Celsius scale, and we have the Fahrenheit scale. And between the Celsius scale and the Kelvin scale, there are 100 degree division between the lower fixed point and the upper fixed point. So if this is a temperature scale, the lower fixed point, we have 2 points. The lower fixed point for the Celsius scale, if you look at the right side is the Celsius scale. The left side is the Kelvin scale, what we call the thermodynamic scale. So this is called the Kelvin scale. So for this diagram, they are showing or demonstrating two scales. Now on the right is the Celsius scale. Now on the Celsius scales, we have the melting point, which is the temperature of ice, which is 0 degree, and we have the boiling point, which is 100 degree. Okay, now below 0 degree, at this 0 degree is positive 273 for Kelvin. Remember, this is not the 0 for Kelvin. If you read 0 for Kelvin, is negative 273 for Celsius, for temperature in Celsius. So 0 for Kelvin is negative 273. So if you move from 0 in Kelvin scale to 100, this one would have reduced to or increased to 173, because you move 100 up. From minus 273 plus 100, you get 173. Then if you move another 100 up, Kelvin will be 200, and Celsius will be negative 73. So if we move 73 up, we would have reached 0 degree on Celsius and 273.15 on approximately on the Kelvin. If you move another 27 up for Celsius, that will be equivalent to 300 of Kelvin. But I'm going to give you formula for converting them. Okay? Before we do this example, let me write the formula out. On Kelvin scale, if I want to change temperature in Kelvin is equal to temperature in degrees Celsius plus 273. Okay, let's see. If you want Kelvin, anything in degrees Celsius plus 273. Yeah. So for 0 Celsius, you add 273, you get 273 on Kelvin. So temperature in Kelvin is connected with this formula. If you want to change, we can call this equation 1 for temperature. And then if you want this one, it will be this minus this. So temperature in degrees Celsius, if you want temperature in degrees Celsius, that will be temperature in Kelvin minus 273. And let's take a look at an example. It says convert the following values between the Kelvin and Celsius scale temperature. 0 Kelvin will be how much? So you want to change to degrees Celsius. And we say if you are changing to degree Celsius, 0 Kelvin will be what? So 0 minus 273, right? That will be what? If you are changing to temperature in degrees Celsius, that will be negative 273. Okay, it's actually 273.15, but we always approximate to the nearest whole number and leave it as 273. So that's how they got this negative 273. Now the second one, they gave you temperature in 0 degrees Celsius, and they want Kelvin. So 0 degrees Celsius, you come here, they want Kelvin. Here's our formula for Kelvin. This one is for Kelvin. So if you want temperature in Kelvin and it's 0 degrees Celsius, you say temperature in Kelvin is equal to 0 plus 273. And that will give us 273. Positive, as in positive 273. That's what we're going to get. That's how they got this 273. Okay, although they did state the formula the way we stated it. So you get 273 Kelvin. You get 273 Kelvin. So here you put Kelvin to show that it's in degrees Kelvin. This one you put degrees Celsius to show that your answer is in degrees Celsius. Okay, so that's that for that. Let's move on quickly. Now the gas law. The gas laws. Pressure and the gas laws, the pressure and the volume at constant pressure. At constant temperature. This is called the Boyle's law. Right? Robert Boyle. This is called the Boyle's law. We're going to talk about that. Okay, the Boyle's law states that for the volume of a fixed mass of a gas, the Boyle's law says that for a fixed mass of a gas, the pressure varies inversely to the temperature. Varies inversely to the volume. The gas law. We have different aspects of the gas law. We have the pressure law, we have the Charles law, and we have the general gas law. But the general gas law you're going to learn at a higher level. But let's just focus on the very popular one for IGCSE. So if we have, this law states that the pressure of a given mass of a gas, the pressure is inversely proportional to the volume. In variation, when we say inversely proportional, we have to write 1 all over V. We have to write 1 all over V. At constant temperature, temperature must be constant. Meaning, the temperature will be same throughout. It cannot vary, cannot increase, cannot decrease. You have to keep it at a constant value. So if the temperature is same, let's say room temperature, let's say 25 for example, throughout your experiment you have to keep the temperature to be around 25. So if the temperature is same, if you keep it constant, the Boyle's law, what we call the Boyle's law, this is very popular with IGCSE papers. The Boyle's law Okay, this is the first gas law that or the second gas law. We looked at pressure law before in a graph. When we pressure law, we plotted pressure. Pressure is directly proportional to temperature. Volume was constant. So we plot a graph. We show the graph today, where they plotted pressure on this side and temperature on this side, and then we had, I'm just showing you what we saw before, and then we had the graphical line coming to touch here at negative 273, the absolute zero value, touching here at negative 273, this place. Okay, this one was the pressure law. So whenever we have a graph of pressure varying directly as temperature, this is called pressure law. When we have volume vary directly as temperature, this is called Charles law. Charles, volume and temperature. These ones, they are direct variation, and their graph are like this both. The only difference between this and this is that I take the volume and put V here. Every other thing is same. Put the V here, it becomes Charles law. This one is called Charles. Charles law. Why this one is called, when the pressure varies directly as the temperature, this is called pressure law. This is called pressure law. Okay, but the one we're looking at, when the pressure varies, this one, for this one, pressure varies directly as temperature, volume is constant. You can see there are three parameters, PVT. For this one, pressure vary directly as the temperature. The volume will be the constant. For this second one, it is volume that varies directly as the temperature. The pressure will be constant. But for this Boyle's law, the third law, the pressure varies inversely, not directly now. Inversely. When they say inverse variation, they means one all over. Inversely. So when the pressure varies inversely as the volume, then the temperature will be constant. Temperature, the third parameter, will be constant, because this is between pressure and volume. So temperature will be constant. Now in variation, if you introduce the equal to, then we have to introduce the constant of variation, K. Constant of variation, K. So you say K times 1 over V. So we have P is equal to the K, which is the constant of variation, over V. This K is the constant. Remember, this is the constant, which will represent the constant temperature. This is the constant, which absolutely represents our constant temperature that has been told as a condition for this case. Now, if we cross multiply, you will see that we have P times V. If you cross multiply, will be equal to constant. Will be equal to K, which is constant. Okay, remember. So if that is true, if K is constant, if K is the constant, then we can say P1 V1 is equal to P2 V2 is equal to P2 V2 is equal to Pn Vn is equal to P anything V anything. Okay, for simplicity in the exam, we just make use of this one. We make use of this one for simplicity. So we say the Boyle's law is P1 V1 equal to P2 V2. This is the formula we use for calculating the Boyle's law, when the pressure varies inversely as the volume and the temperature remains constant. For Charles law, this one, V varies directly as T. This is Charles, V and T. Then you say V, if you introduce equal to, then you have to introduce the constant of proportionality, which is KT. So if you make K the subject, K is not the subject, which is something you're going to learn in math, change of subject of formula. So if K is the subject, so you divide, meaning you have to divide the right side by T so that K can remain alone. You have to divide the left side also by T. So if you divide the left by T, you have V over T. And then here you have KT divided by T so that K can remain. So this one cancels this one. So we have, for Charles' law, the constant is V over T. So the formula V1 over T1 over T1 is equal to V2 over T2 and is equals to Vn over Tn. This is called Charles' law. This is what you need in case you are calculating any problem that has a given volume of a gas that is directly proportional to the temperature while pressure is constant. Therefore, this is Charles. This is what you use for Charles' law in calculations. This is Charles. Then for pressure, it's just to change this V to P. Same T, but we change the V to P. P1 over T1 is equal to P2 over T2. Are you there?
Yeah.
Okay. I thought you're sleepy. Okay, this is a pressure law. This is pressure law. So I just summarize them here. Whatever they say there, we only look at calculations. So I've given you the law. This is pressure law formula. This is Charles' law formula. And this is Boyle's law. This one. Boyle's law. But in IGCSE, I think the focus is on the Boyle's law. This one. Boyle's law. More. The focus is more on this one. Okay. So that's that. Now if you look at, we say the pressure is inversely proportional to volume. Now look at the logic. Here you have a big volume. The whole container is the volume space for the molecules. So since the volume is big, the pressure will be low. Why? Because pressure and volume are inversely related. Why? Why is that? Because there's so many space for the molecule to move. Before they hit each other, it takes a while. There's so many space. So the collision is less. Speed of the molecule is less. Average kinetic energy is less. And then the collision is less. Therefore, pressure will be less. Or like if you have the pressure, you bring a piston to push. You push the molecule down. So the only space they have left is now here. This small one. If this is even less than half of the whole thing. So all the molecule, all of them are now concentrated in a small space. So this one will now give you greater pressure. Why? Because the volume is now smaller. So for smaller volume, Boyle's law, according to Boyle's law, that's why they are inversely related. Small volume gives bigger pressure, big volume gives smaller pressure. That's the inverse relativity. Is that okay? Now here we say for more frequent collision of the gas molecules with the container wall, as the particle have more energy. Yes, the more collision we have, the more the gas they collide with each other, the more the energy. Okay, let's move on quickly. So all these Boyle's law, you see now they are really explaining the Boyle's law. I've done this already. The pressure varies inversely as 1 over V, and then they jump to P once. Most times the student will not know how they jump from here to here how this formula became this P1 Vy equal to P2 V2. But if you look at what I did, I showed it step by step how we got to this formula. P1 V1 equal to P2 V2. Okay. So, having known the formula, the P1 is called the initial pressure in Pascal. The P2 is the final pressure in Pascal. The V1 is the initial volume in meter cube, and the V2 is final volume in meter cube. So once we know this, then we're able to plot. Now, if you plot a graph of volume against pressure, this is what you get. This is what you get. Volume against pressure. If you have the graph, V against P, you have this graph. But if you plot volume against 1 all over P, you now have a straight line graph. If you do volume against 1 all over P, if you do volume against 1 over P, that's the reciprocal of P. If you do volume against the reciprocal of P, you have this one. You now have a straight line graph. You have a straight line graph. Okay, so this is what you get when you plot the graph of volume against pressure in Boyle's law. Okay, so here are questions. So this is the graph, volume. You see volume. When P is 1 all over 5, V will be 1 over 1 all over 5, which is 5, because they are inversely related. So when P is 1 all over 5, to get V, you just say 1 over 1 all over 5, you get 5. If P is 1 all over 4, V will be 4. They are inversely related. Is that okay? That's just the logic. And that's why we get this type of exponential decay graph. Okay. Next one.